Hello and welcome back. Today we'll be doing question 1 from the 2003 Step Paper 2. This is a question about simultaneous equations, however I will be solving these using a matrix method. Let's get started. Question 1. Consider the equations ax take y take z is equal to 3, 2ax take y take 3z is 7, and 3ax take y take 5z is b, where a and b are given constants. Part 1. In the case a equals 0, show that the equations have a solution if and only if b is equal to 11. In the case a is not equal to 0 and b is equal to 11, show that the equations have a solution with z equals lambda for any given number lambda. Part 3. In the case a equals 2 and b equals 11, find the solution for which x squared plus y squared plus z squared is least. Part 4. Find the value for a for which there is a solution such that x is greater than 10 to the 6 and y squared plus z squared is less than 1. Pause the video now to have a think, and once you're ready, restart to see if you were correct. Let's get started with part 1. Firstly, we'll define the matrix A to be A, -1, -1, 2A, -1, -3, and 3A, -1, -5. These are the coefficients from the set of simultaneous equations above, meaning that using matrix multiplication rules, we can write that A multiplied by the vertical matrix X, Y, Z is equal to the vertical answer matrix 3, 7b. Now we can calculate the determinant of A while substituting in lowercase a is equal to 0, and this should give a determinant of 0. This means that A is singular, and therefore the equations have a solution if and only if the equations are consistent. To solve for consistency, we can take the upper right 4 values of this matrix A, that is the submatrix -1, -1, -1, -3, and multiply that by the vertical matrix Y, Z, and this should be equal to 3, 7. From this we can see that Y and Z are equal to -1 and -2 respectively, and therefore the matrix -1, -5 multiplied by the matrix Y, Z must be equal to 11. Thus, the equations have a solution if and only if b is equal to 11 as required. Now, let's move on to part 2. If we evaluate the determinant while a is not equal to 0, then we still have that the determinant is equal to 0. Since b is equal to 11 is consistent, we therefore have a solution for z is equal to lambda for all lambda as required. Now let's move on to part 3. Here we have a is equal to 2 and b is equal to 11. Therefore we can write 2, -1, -1, 4, -1, -3, 6, -1, -5 multiplied by x, y, z is equal to 3, 7, 11. From here, we can solve under the assumption that z is equal to lambda to give x is equal to 2 plus lambda and y is equal to 1 plus lambda. Therefore, x squared plus y squared plus z squared is equal to 2 plus lambda all squared plus 1 plus lambda all squared plus lambda squared. We'll call this k, although bear in mind that we can optionally expand and simplify the brackets to give 3 lambda squared plus 6 lambda plus 5 is equal to k. From here, we can use symmetry or calculus to determine that the minimum value of k occurs when lambda is equal to -1. Therefore, the minimum value of k is equal to 2, and we have x is 1, y is 0, and z is -1. Now we can move on to part 4. Here we can choose any value of lambda that gives y squared plus z squared is less than 1. For example, lambda is equal to negative 1/2, which gives y squared plus z squared is equal to 1/2. This also gives x is equal to 3 over a, and thus we can change a such that x is definitively greater than 10 to the 6, for example by using a is equal to 10 to the negative 10, giving us a solution that fits the requirements. If you liked our video, please like and subscribe, and we'll see you next time for some more fun maths problems. Thanks for watching, and goodbye.